All right. Hello, everyone. I am Kyle from the UBC Game Development Club, and I'm here to give a presentation on shaders. So this will be all about shaders. It'll kind of be a really general overview on how they work and what they do. And then at the end, if we can, we'll actually get to writing our own shader and talk about how they kind of work in Unity specifically. So a lot of info for this presentation is based around Unity, but I tried to keep it really general. So a lot of the stuff you could totally apply to other engines or even, working on graphic stuff kind of directly. But kind of with that, I think we're ready to kind of get started and ask the big question: what are shaders, right? So you might be familiar, you might have used them before, but in general, kind of a bit of a definition that captures all of them would be it's kind of like functional code that lets us interact with the GPU or create visual processing effects. That is the main kind of function of shaders, at least in Unity. This kind of code could have, different names in other applications, kind of visual accelerators, but specifically kind of for this presentation, we'll call them shaders. So I'd like to kind of get started with the most common use of shaders because they actually have a lot of uses. More uses than, probably have even been discovered, and there's a lot of really crazy stuff you can do with them. But first, in order to kind of talk about the main use of shaders, which is just regular scene rendering, we kind of have to talk about how scene rendering actually works. So for most programs that kind of run in real time and have a constant frame rate that they keep up, every frame, it puts something on the screen, right? So every single frame, it has to do some calculations and decide what pixels it would put all across the entire screen. Specifically for like games or scenes and that kind of stuff, it uses kind of data that's stored in an instance. Like, for example, if you think of a scene in Unity, it has a bunch of objects in it. All that scene data, it's going to use to determine what to draw on the screen, right? The data has to be translated, though. It's kind of hard to know, well, you have an object, you have a circle. What does that mean in pixels on your monitor? There's a lot of calculations that kind of have to go into it, a lot of algebra that, your system does in order to make it display 3D things kind of effectively and efficiently. So usually it uses the GPU to help with these calculations, like the data translation. And that's kind of usually, or originally, the purpose of the GPU was specifically to speed up these kinds of calculations because so many programs had to do them and it had to happen so often, it seemed like a good thing to kind of make a separate kind of processor for. So I mentioned that it uses the data from an instance, but let's talk a little bit more about that. So what exactly does this data that it needs to look like, or that it needs look like? Well, you can have the 3D instances. So back to the kind of the example of a Unity scene. In a scene, you've got a bunch of objects, right? And some of those objects have mesh renderers, some of them have other things. That's kind of the data that's held in a 3D scene that we need to send over to the GPU so it can figure out exactly what to draw. So out of that scene full of 3D objects, all those 3D objects also contain a bunch of data, right? They contain the vertices, little points, and their relative positions, as well as where they're connected, right? Edges and vertices. That's always stored in like the 3D kind of model data. It also has stuff like maps, although they're usually not held in the 3D model. They're something separate that we kind of put on there. But maps are kind of like 2D images that kind of have different data for different parts of the object. And that's pretty much, in general, maps can do a lot of different things. But later in the demonstration, we'll kind of get into it. And I can show a bit more of the maps. Maps might include something like, if I open up a sample kind of Unity scene here, stuff like a texture, right? So if I have a model and this texture kind of goes on it, this 2D kind of image here would be a map of a sort, right? It has a bunch of colors, and those colors have got to go somewhere. Somehow they're going to translate into our 3D object when we actually draw it on the screen. But how exactly we make that translation, we kind of have to specifically mention, probably in the vertex data of the mesh as well. So this would be a 3D mesh. So this is an otter that I made. Pretty cool. But as you can see, all of these are little points, vertices, and they have edges between them and faces between edges. That's the data that's held in the 3D kind of models. And that's the data we got to send to the GPU. So kind of going back to presentation. So these calculations have to be very carefully and very quickly performed to figure out what we actually end up drawing, right? So let's talk a bit about when does it actually do this, right? So here's kind of what the pipeline could look like. In Unity, it's something like this. In most similar functions, most engines, it's something similar. So first, it has to run all the update functions. So every object that has some special code that it wants you to do, it has to run through that and execute all that code, right? Once it's done with that, it then has to take all the object data that it needs to and send it to the GPU. The GPU does a bunch of calculations to figure out exactly where it goes on the screen, and then it puts the 2D image on the monitor. The GPU kind of does that. That's the general pipeline. In programs that aren't Unity, it still follows a similar structure usually. It'll have something like a big super loop that'll loop through, and every single frame, usually at the frame rate of 60 or whatever you set it to specifically, it'll do all this stuff. It'll run all the updates it needs to simulate the game logic or the program logic, whatever you kind of have. Then it'll run this draw section where it'll send a lot of data to the GPU. And that's pretty much it in general, kind of for the pipeline. So this would happen once every 60 seconds or whatever you set your frame rate specifically kind of to be. That's kind of how often it would try and update that. Of course, this is limited by how fast it can do all these things, right? And how fast the GPU can actually put things on the screen. But in general, it would try to do these frames, and in theory, as quickly as it could. So let's talk a bit more about the GPU and why exactly do we need it? So it really is kind of a separate processor from the processor that we normally use on the computer to do a lot of logic calculations, right? It's a whole kind of different chip that's built specifically it's built to do some things specifically very quickly, right? And what exactly those things are is typically a lot of graphic stuff, like turning 3D vertices into a 2D image, a lot of the different vertex calculations that it kind of needs to do. These are essential in modern day graphics, but we didn't always used to have GPUs. I'd guess almost 15 years ago, computers would just have a regular processor that would just do all these things. But the GPUs were made as kind of a way to accelerate it and make it way better. So if you ever see computers that say they have integrated or designated graphics cards, that's kind of the difference, right? Is that if it's an integrated graphics card, that's just you have one chip. It's just that one CPU that's doing all that stuff and it's doing its best. But the designated is you have a whole separate GPU, right? So almost every computer nowadays has a designated one. Using the integrated one's very old. But that kind of shows just how important it is. Graphics ends up being a huge part of modern applications, and speeding that up ends up speeding up computers by a ton, right? So some can be optimized for specific other things, right? Some may be really good at drawing certain kinds of graphics, or you could even have GPUs that are good at doing different calculations entirely. Not just things for visual graphics like 3D models, but also for things like AI, right? If you've ever heard of the AI CUDA chips, they're GPUs specifically made to accelerate some AI calculations and that kind of stuff. So you could make GPUs to do other things very quickly as well, in theory. But it runs in parallel with your processor, which means as your processor is doing anything or whatever else, the GPU is also managing its own data and doing its own thing, which can help to speed things up. That's kind of the purpose of it. And most modern graphic libraries automatically utilize this without you kind of having to, explicitly say, go and use the GPU. So if you're even if you're using a 2D library or just automatically in Unity, it'll probably be sending those vertices to the GPU to do the calculation. It won't be trying to do them all by itself and or just on the processor and being super slow. And kind of like I mentioned, as they could be used for different things, they can also be used for things completely unrelated for graphics. And we'll talk about that a bit later, actually, in the presentation. But so something that we actually see that recurs a lot in GPUs is they were kind of made specifically to take in 4 values, 4 floats at once. And they're really good at doing operations between those 4 floats. Now, as time goes on, this might change to be 8, or the number might change specifically. But the kind of in modern GPUs and in shader programming, at least in Unity, we see a lot of 4 vectors and 4 packed arrays. And that's specifically because of the way the GPU is made with its registers. It was built to compare 4 things very fast. So what could these 4 kind of values be? Well, in the case of graphics, it could be a red, green, blue, and alpha value, right? It could be X, Y, Z, and W for rotation. Or maybe Y1, X1, X2, Y2, if it's like a 2D game or something like that. We can make these values kind of whatever we want. So the shader actually decides what these values are, how they get sent to the GPU, and what the GPU does with them. So usually in default shaders, it'll pick some of these stuff. It'll pick the red and green, blue, alpha, X, Y, Z, W. But if we're writing our own shaders, we can also choose what values we actually send to it as well, right? These values could be something completely unrelated to position or X, Y, Z, W. And really, they can actually be anything you can think of that would really work well just with a bunch of 4 value calculations specifically. So now let's actually talk directly about the shaders specifically. So in Unity, they are the scripts that help us kind of apply different visual effects, but they can also interact with the GPU in other ways in Unity. And most similar programs kind of are the same. So the shaders figure out exactly what your GPU is going to do. Like in code, what code will your GPU run in order to do these calculations? So if you have a really advanced shader, like maybe even the default Unity shader or ray tracing shader, it's mostly going to be a lot of complex calculations with light, right? Where's the light coming through? What blocks the light? Where does it reflect? And the GPU can help speed this up a lot. So it can also help us modify the data a lot before the GPU, or before we think about any visual calculations, right? If we wanted to modify a shader to make it so it considers all vertices a little bit to the left of where they actually are, we could totally do that. That wouldn't be something super, unknown to the GPU. It can modify and mess with the data, and during the demonstration, we'll actually see that a bit. But because the GPUs just kind of take 4 values, shaders can be used for a huge number of things, and things that probably we haven't really thought of before until now when GPUs have got really fast and really versatile. Using them for different parallel kind of calculations could be super important. However, some shaders can be extremely complex to make and do. And I'll kind of explain a lot of the different kinds of shaders in Unity later, but some of the algebra that you do have to consider in order to make visual like shaders that do really cool effects, it can sometimes be extraordinarily difficult. But one of the things that shaders can often kind of be used for, so here we'll actually see a bunch of different example shaders in Minecraft, and all of these will take in the data of where the blocks are. The blocks are actually stored as a number of triangles, all kind of set up towards each other. If you kind of think of it, if you have a square, you could break that into 2 triangles, and it's really easy to mess with triangles to change the perspective. So that's actually kind of how Minecraft draws itself on the screen using the GPU. And so it's kind of, in Minecraft, it's a lot simpler to figure out how the light kind of bounces off things, right? The GPU might get the position of the light and then decide how to brighten certain pixels based on where the light is. So here we'll see, though, that there's a lot of different ways of doing that, right? There's a lot of different ways to consider where the light's coming from, how much the light leaks into different areas, what it really does. And all of these can be kind of programmed explicitly, and I'll have different like specific uses in the program. So here sometimes you don't like directly see all the differences between the shaders. Some of them do definitely look very similar, but a big difference that you might notice is in reflection. Reflection is something that shaders have always been trying to do because that makes things look very realistic, but it's not always easy to do. If you think of ray tracing and the RTX on, RTX off, the biggest kind of difference between them, and I'll kind of show that here, is the reflections. So notice that with RTX off, it's just, some vague light reflections coming through the window, but it tries not to be too specific, right? It's just generally a bit brighter because the light is near there. But meanwhile, with the ray tracing on, it tries to get everything. It tries to figure out exactly where the light will bounce and how. And it kind of does this by, getting a vector, pointing it where the light should go, and then seeing how it reflects and then drawing it on the screen kind of appropriately. Something to notice is that it's drawing things there that aren't actually on the screen in the reflection. Like, notice how the top of the tree is kind of apparent there in the reflection, but the top of the tree isn't in the top of the screen. Well, to do that, you do have to consider a lot of data that isn't on the screen, and you have to think about where exactly things will bounce. And those kinds of calculations can be super complex. But also, they give us lots of room to do cool and unique things, right? You could have the reflection show something different from what's actually in the game. If you think about it, like if it's a mirror or the reflection on the ground is something different than if you looked up. And you could do that all kind of in the shader, because the shader gets to decide what's actually drawn in the reflection. But that's not kind of all that you can use shaders for. I mentioned they could be used for other things. Well, there was a very popular game, it came out 2020, but it gained popularity, about a year ago, called Noita. It was a super cool, unique idea where you kind of go into this huge set of caves and cast a bunch of magic, and it was very difficult. But the thing that was so unique about it was that it had very in-depth fluid mechanics, right? So it was a pixel art game, and it had pixely kind of fluid. And the thing is that this is normally really hard to do. So if you think about it, unfortunately, this is the best GIF I could find for it. As you do things, the different fluids in the game are kind of modeled by a collection of pixels that kind of fall down and they roll and they do things. It uses the GPU specifically to accelerate and figure out how these pixels should fall, where the liquid should go, and how they should interact with each other. And the result was something really, really amazing, right? This game ended up being super popular despite being made by such a small team. But you can have liquids interact, and you can have liquids actually flow the way we would expect them to in, almost similar to real life. Of course, it is 2D, which is what really made this possible. 3D fluid mechanics is still an extremely difficult and high-level kind of problem that GPUs are trying to solve, and as they get faster, they get better at it. But in the case of 2D and simple pixel art physics, fluid mechanics was actually kind of interesting. So you can almost actually see in this GIF, character, you're a wizard in this game. The character blasts some water, and the water falls in the fire and in the acid, and it interacts with it. But every single little pixel of the water and the acid and the fire is individually made with its own kind of physics, right? It knows that when a single pixel of water lands on a single pixel of fire, it'll put it out, right? And it knows that when a pixel of water goes into a pixel of acid, the entire kind of strength of that acid is reduced. And those kinds of physics calculations can make for really unique things. It was kind of, this was kind of ways that no one really thought of using shaders, that now we realize we can use them in these ways. So this also led to some kind of unique and interesting things where there were so many different pixels, all singularly simulated, that the tiniest little flash of one molecule coming out of one piece of lava could end up interacting with the character and killing a character, which is pretty unfortunate. But it let things happen where there were tons and tons of particles on the screen, and yet the game still wouldn't slow down. Normally, if you had tons of little things being simulated, the game would just freeze up and take way too long. You have to loop through every single pixel. But by using the GPU parallel kind of processing, we were able to, the creators were able to actually make things run quickly and cool. So that's a really cool game, and I would recommend checking it out if you're really interested in how you can use shaders creatively, because it is an amazing example of how they're used super creatively. In a lot of other games, it hasn't really been too common. Video games specifically, but right now, shaders are the biggest use of shaders that's non-graphic has been AI. But there's lots of other uses that potentially haven't been discovered yet, which is why I thought it was very appropriate for an emerging media kind of presentation. And that's kind of it for my slide set. But now I'd actually like to go through in Unity kind of making a shader and what they mean. We'll take a look at the default shader, and we'll kind of talk a little bit about how the shaders could work. The literal shader code that does everything very specifically can be extraordinarily complex. So usually, at least when you get started, it's a good idea to go through a bit of an abstracted kind of version of it. So that's kind of what Unity tends to do. Let's bring back the scene with the otter. So when I say that, I mean Unity has its own shaders. So if you go to create, you'll notice you can actually create shaders. And some of these are very complex, but some of them make it a bit easier. They let you write shaders in more human readable language, other than just like pure assembly code, that still gives you the ability to do anything in shaders. This is a gigantic strength that Unity has that a lot of other engines like Godot and other things, they let you make shaders, but they're not nearly as good as Unity is, which is why a lot of people say Unity is an amazing visual effects engine. But in other engines anyway, this stuff will still be similar. It's still the same kind of thinking that shaders will require. So you'll notice we have a couple options here actually for the shaders. Standard surface shaders, unlit, image, and a couple of them. Oh, here, let me bring that back. So the standard surface shaders are the regular lit ones that take in the light and they do something fancy with it. This would look most like a shader in default Unity, or earlier when we were looking at those Minecraft shaders. That's kind of what this would look like. Then there's unlit ones that don't consider light and just think about the vertices and where they are. That was actually, it's an older kind of style of shader that would work for a lot of kind of older games or applications where you don't really care about, really dynamic, interesting light effects. Image effect shaders are a bit different. They only, after the GPU has done everything and it made an image for the screen, it'll go through and it lets you modify that image. So it'd be really good for applying an effect to the whole screen. Like if you wanted to make the whole thing bloom or the whole thing, go black and white, weird, funky colors. The compute shaders are the ones where it doesn't directly involve graphics. You kind of get to decide, okay, shader, I want you to calculate this completely unrelated thing, like the fluid physics or the bullet physics or something, and then give me back the result. As a result, making compute shaders is extremely difficult. There's a lot of, if you ever go on the internet and you look up, compute shader tutorial, there's a lot of jokes about, you need a math PhD in order to make it. And it is true, the math is really difficult, but it's still worth investigating if you think you have a really good idea of something that could be done in parallel with a shader. Or if you think that you could make a shader that really works well, compute shaders can be extraordinarily useful. And of course, the ray tracing shader. We talked about ray tracing a bit before. This would just kind of help to facilitate how exactly that works. Unity makes ray tracing work pretty well. But for this tutorial, we're going to focus on the unlit shader because it's really simple and it kind of gets us started, and it still lets us do useful things. So I'm going to create a new one, and I'm going to call it bug effect. So I'm going to make it do a bit of a funky bug effect, but before that, we're going to modify it a bit and kind of see what happens. So let's open this up, and I bet it's going to open in my Visual Studio. Let me just drag that in. Wait, what? All right, let's see here. Where it is. Okay, and let me try to see if I can open this in a new window. There we go. All right, so bug effect shader. Here we are. So this is the default kind of shader that we see in Unity. So as soon as you start a shader, this is what it will contain. The first thing here is the name of the shader. So right now I have it unlit/bug effect. That's actually where it will show up in Unity. So if I bring back up the Unity, and now if I go to a material, first let me create a material. If you're not too familiar with Unity, it might be worth kind of noting, I'm going to call this bug mat, that the meshes get materials on them and the materials decide how they look. So really, the material is actually the shader. That's kind of how it works. So you notice right now it's on standard, but I can actually go into unlit and I can select a bunch of these ones, and bug effect is right there because I put it in unlit/shader. And there's a couple other ones that they kind of already have here for unlit, but I'm going to select bug effect here. So we'll notice that this is a bit similar to the Unity default, well, it's not very similar, but it has a texture that you can put in here and a bunch of other stuff. So let me go back to the standard actually, if it'll show up here. There it is. So if we go back to the standard, this material is a shader in general, but it's a specific instance of the shader because you can program them with parameters, right? Let's say you want two objects to use the same shader, but one object is a bit more red than the other one, right? Then you would have two separate materials that both have the same shader, but have different things here, right? So you'll notice there's albedo, metallic, smoothness. All these things are used to determine where the light bounces off to make the shader look really cool. But if we go instead, oh, that's the rendering mode. If we go instead back to our unlit bug effect, we'll see that it only doesn't have nearly that much stuff. It just has texture, tiling, offset, and a none for texture. Render queue stuff, all this, it's pretty small. But we can actually see that stuff in our bug effect shader here. Right here, just a main text, it takes the texture. That is the texture kind of section that we saw before. So something that's kind of worth noting, by the way, is that this isn't written in C#. The shaders are written in something called Shader Lab, which is a bit of a shader language that kind of lets you write down the stuff. It has a lot of versatility, and you can write down anything you want to do, but it also makes things readable, and it also makes things easy to kind of understand. There are editors that can actually help you write in Shader Lab way better. I think one of them is called Amplify. It's totally worth looking into if you think you're interested in getting into shaders a lot. But yeah, so first we've got the properties, right? These are the kind of things that like parameters for the shader that people will input in order to determine what the shader looks like. Your program could input these, or maybe you put them in right when you start the scene. This includes things like the albedo or reflectiveness or whatever we kind of have the material has. So this part here actually gets into what the real shader is. So right here, this kind of tags render type opaque. Before we actually get into the real code that the shader executes is we tell the editor when do we render this stuff. So for example, the render type kind of helps us determine what order we render things in. So right now it's opaque. If something is opaque, then we only want to render it if it's in front of all the other objects, right? If something's transparent, we want to render it we want to render the stuff behind it first and then render the transparent object. So that kind of stuff could be kind of done here, and we'll take a look at changing that a bit later. The LOD is level of detail. That kind of determines how far the GPU goes to determine details and stuff like that. If you're programming something very specific, you might have to change this, but in general, it's not completely necessary unless you feel like, well, that must be the issue, is it's not enough detail. So kind of moving on, we have this pass chunk, and we'll notice that pass chunk is kind of like our last bit here. So this is what's past the GPU right here. And this code gets way more codey. It starts to look like C language. Well, notice we do the CG program. So this is kind of the GPU program right here. And we get a couple parameters for it. A vertex, vert, a fragment, frag, and this kind of fog thing. So these usually you kind of want to keep the same. There's a lot of different things or ways you can modify this kind of chunk, but for those, it gets more complex. So for now, we'll kind of leave that. But something you'll notice that we do here is we include Unity CG, so like a couple of libraries. So this probably looks a lot like C code because it kind of is C code. And something to notice is that this script is not a monobehavior, right? If you had a monobehavior script, that inherits all the stuff from Unity, and you can do update, and you can do all those fancy calls. But this is just a regular script, right? Or not regular. This is just a regular kind of piece of code. So that's why we kind of have to include Unity functions so we can do a lot of the kind of helpful things that Unity will let us do. So next, moving on, we've got a couple of, scrolling down the wrong one. So we have a couple of structures here that are going to hold some data. So we've got an app data structure that'll kind of talk about, or that'll kind of hold the data that we send in from, or the initial data that we kind of send in from Unity. So it's got vertexes and UVs, which are both used to draw a 3D model. If you know in a 3D model, you kind of have to decide what parts of a texture map to what parts of the model. That's called a UV map. And here, we've got to send the UVs into the GPU so it knows what parts actually map, right? Then we've got some vertex data here, or vertex data. that we are going to send into another part. So I'll kind of explain that a bit in a second. But you'll notice that we take the text chords and the positions. So this way of kind of assigning things, notice how we go UV and then we put like a colon and then this, is a special kind of assignment that we use for shaders to kind of say, this maps to this, right? Unity has a bunch of big keywords for what means what in like the editor, or not the editor, in like the engine. And here we're kind of grabbing them. So if you want to do something super cool and super unique, it might be a good idea to look up these and see what info we can actually get from it, or perhaps even mod Unity with an add-on to get more info. But yeah, this stuff can be pretty interesting. Something that you'll notice is that this data is of type float4 or float2. This is what when I was talking about the packed array, right? It's an array of just 4 float values. That's all it is. But it's specifically 4. And that's to make it work specifically in the 4 registers kind of set up to do those things in the GPU. We also have float2s. Of course, using those specific numbers kind of helps the GPU figure out what to do. But this is mostly like putting it in a float4 instead of just putting it as 4 values that we just pump in. Makes it quite a bit faster for the sake of like the GPU accelerating stuff. So now down here, we actually kind of get into the real functions that we're going to be doing. So one thing up here is that notice that we call vert and we do frag here. We're kind of like calling functions. Down here, we're actually defining them, right? So down here we have vert, we give it some app data, or I guess Unity gives it the app data, and it does a bunch of stuff for that. So it does this Unity object to clip pose, which determines the actual position of like where it is based on the Unity scene. And we take the texture and we figure out how the texture is going to go on it, right? So in the vertice kind of function, we're just focusing on the vertexes, where are the dots, where are the faces of this mesh, where we're going to put stuff, right? But then after that, we go through the frag function, which takes in that vertice data, the V2F, so it takes it in, and then it'll actually apply the texture. So here, it goes fixed call is equal to, this is another Unity function that we can use, that'll kind of take the texture and the UVs, and it'll put the texture on the UV map. So therefore, it's just putting the texture, or it's determining where the texture actually goes right on the mesh. So that's pretty much it. So you notice I skipped a lot of this fog stuff because that's just, extra, if you want to add fog, and then it kind of returns the color. So that's kind of generally how the shader kind of seems to be working. So if we want to modify the shader to do some fancy stuff, we can mess with lots and lots of this code. But we're going to focus on for now just changing the stuff in the vert and the frag functions, right? If we want to change something with a vertice, we'll probably change it in the vert function. If we want to change the color, we'll probably change it in the frag. Adding on more functions and doing way more fancy stuff is totally within the scope of what a shader can do, but very complex. So out of the scope of this presentation specifically. So let's, first let's actually see what it looks like. So if I open up Unity, so here I have the bug mask, right? I'm going to put a texture here. So this was one of the, I guess if we head back here, notice here it says none texture. That's like a texture kind of setting. And here in the bug effect, we have this main text. That's the texture, right? Hold on, let me undo that. So if we take this main text, you'll notice that somewhere we should use it. Yeah, down here, we actually use that texture. So let's see what it looks like. So if I just drag this texture in, notice this is just a regular PNG. Now I have the material with a texture on it. And let's drag it onto our otter, and boom, that's kind of what it looks like. So it looks kind of, you'll notice that one thing about the sunlit shader is that there are no shadows that it casts on itself at all, right? Which kind of makes it look a bit strange. If instead we created a new material and called it default, just to compare, I spelled default wrong, but that's okay. If I drag this into the albedo map, and then I put this on there, you'll notice it looks way better. It actually shows where the light reflects off certain angles and where it doesn't off other angles. That's all that fancy Unity metallic smoothness. It has tons of different parameters that it puts in its default shader to make it really good. But that doesn't mean we can't make a cool shader as well. So let's put back on bug material. So also, here I'm specifically talking a lot about stuff in 3D. But in 2D, shaders also have a really interesting use. it does similar stuff where it figures out where the positions are and where that means it goes on screen. And like I mentioned in Noida, using shaders for that kind of fancy stuff is super useful. But yes, I just don't want to discourage people from thinking that they're only for 3D stuff specifically. But let's start modifying this. The first thing I want to do, I'm going to take off all this fog because I don't think we need the fog. We don't have fog set up, and it's not really helping us. So just to make things look a little nicer, let's remove all of the fog here. So why don't we get started with a little bit of modifying the color. So let's try modifying the color specifically. So what if we added up here a little tint? Let's go underscore tint, or where is it? Yeah, so here we get to decide the name of this kind of variable and what it does. So I'm going to call it tint color. And then in these brackets, this stuff is just for like the Unity editor and what it actually, what it has by default, what it displays to the user. So I'm going to want it to display tint color to the user. Let's go bracket color, should capitalize it. So it's of type color, just to let the Unity editor know that. And one way to define colors is just like that. So here I just set it to default white, all but ones, just kind of for this part of it. And something else that I think we might want to do is let's try making it transparent as well, because I mentioned the transparent rendering modes. So here I'm going to go transparency, transparency, and this is going to be a value that we'll take, just a single value, and we'll make it a range between 0, 0.5. So this range stuff and all the stuff here I'm doing, actually I'll make it go between 1.0. This stuff is mostly just for the Unity editor. So no need to worry too much about how it actually displays, but we'll take this transparency value here and we're actually going to go down and use it. So one of the first things we have to do though is I mentioned this tag was opaque. Well, now we have to be careful. We want to say that it's transparent because Unity has to know, if it's transparent, I got to draw something behind it and in front of it, right? If you have a window, you got to know what's behind the window as well as what's in front of it. So I actually have to change the render type there. And also, I'm going to add it to, so Q is equal to transparent. So I'm also adding it to the transparent Q, which, like I mentioned, so what order things are kind of drawn in. And this might be important for like deciding, or when it draws the transparent stuff. And here, I'm also going to add another little bit of Z-Right off. Oh yeah, one thing to note, and hopefully I don't do this and mess up, is that there are no semicolons at the end of lines, because it is in Shader Lab. That always gets me, because I'm used to writing semicolons at the end of every line. So try and be careful to not write that. I've also got one last little bit that I want here for the transparency to work, which is this blend SC alpha 1 minus SCR, or source alpha. So basically, it knows things are transparent, but also how does it know how much of the thing behind it to draw? Well, that's kind of what we do here. You'll notice if you look up blend and SC source alpha, all that stuff, it'll bring you to a huge Unity documentation page that'll explain what different kinds of ways you could have transparency automatically in Unity. And this is just one of the ways. So we'll kind of see what effect that has. So let's take a look at what we want to change here. So the first thing is, so down here, I define a couple of the variables that I actually use, right? So I have a sampler for like the main texture. What I want to do here is I want to have a float for the transparency. And this here, putting this here will kind of map to the transparency that we have up here that we'll be getting from the Unity editor. And also I'll add a float for tint color. Oh, this should be capitalized. For the tint color that we added up here. Oh, and now I am adding semicolons. Oh yeah, because now I'm inside the this part. But anyway, yeah. So that the syntax sometimes is a bit strange, But now, what are we going to do with these? Well, first, I got to make sure I have that right. Yeah, okay. So, what are we going to do with this, color and changing stuff? Well, specifically, we're going to take a look at the frag kind of function here. So here we actually decide what the color is for each pixel on the screen, right? Based on the main texture and the UVs. Well, we can actually mess with this a little bit and say plus underscore tint color. So now we're going to be adding the tint color directly to it, right? And if it goes over 255, then it'll just be, pure white. So now that we're kind of adding this, so we could also consider, averaging out the values. We could consider multiplying them, whatever we wanted, all for different effects. But for this case, we'll just kind of add it. So this will kind of actually change the whole color into something else. And I also mentioned the transparency. Let's go to the call kind of has a bit of a color part to it. It's a fixed 4. That's the call.a. That's the alpha channel. I'm gonna say that's equal to transparency. There we go. So now the transparency there will be set. And the rest of it, I think we should leave. We don't need to mess with the vertexes themselves because here we're just doing the stuff with the color. So let's see what that does. Let's open up Unity, and whoa, there he is. So now he is transparent and we can see through him. So one of the things I mentioned that there was like the Z-Write buffer and there was the Z-Write buffer and the blend alpha. One thing that we might notice is that we can see him through him, right? Specifically for this part of his leg. And that we might change by telling it don't render itself before itself. But right now that's not really too important. So we'll notice that it's transparent. And if we go to the bug material, we'll notice that its transparency is 0.25. And I can increase the transparency or decrease it. But you might say, well, also he's super white. That's because the tint color that we set here, right? We're adding on this pure white. If we change the color a bit, we should notice that he will change as well. If we make it pure black, then there's no tint and he won't change at all. But we can make him whatever color we wish now, make it brighter. We could turn up or down the transparency. And we now have a bit of a tint. And now you can imagine if you messed with these values, you could actually have some pretty cool effects where the colors kind of change over time. Something that's really important to note, and we'll do this later, is that within a Unity script, we can change these transparencies and these tint colors and all these values during runtime, right? So that means we could make him change color while we're running the game, which is super useful. If our shader is prepared to take in certain values, we could decide which pixels of his are transparent exactly at runtime, right? So imagine if you had a character that was like a ghost and could phase through things. You can make them just become transparent in a certain range or in a certain format. But of course, that might be it would take a bit of prototyping and be tough. But as an example of what you could do by writing your own, even just these unlit shaders. Okay, so that was pretty cool. But let's see if we can do some other stuff. So how about let's try and mess with the vertices. So down here we get the vertex data. And we get it, and it's kind of useful, but we don't do anything fancy with it. So let's try actually messing with it quite a bit. So in this app data, we have, so it's app data V. We can actually get the vertexes by going something like that. So for each vertex, the vertex.x, we can mess with that. So why don't we do something funky with it? Like, so in this Unity, so up here, I did the, where is it? The include statement. Oh, here it is. The include unity cg.c. It comes with a lot of useful, fancy functions that let us do useful and fancy things. Oh, whoops. Sorry, I was looking at the wrong. It helps us do a lot of useful and fancy things. So, like, for example, here, it has a sign function, right? And it also gives us access to time. So I'm going to say speed, something like that. So pretty much this underscore time thing is something Unity provides where every single time it renders the mesh, it'll also give the GPU what time it is, right? And this could be in seconds since the last frame. It could be in another form. But basically, we're just kind of putting this in here to have a little bit of a randomness. But I'm going to make this look a bit funky. So vertex.y times Damn. So I need a couple things here for this to actually work, right? I need the vertex y and the vertex, like a bit of data here. So let's oops, but I put a dot there. V dot vertex. So we need speed, amplitude, and let's also add a couple other things. Let's add underscore distance. And let's head up here and let's grab the speed, amplitude, and distance as actually some parameters that we can put in here. So for example, speed, let's call it speed. Let's make it just a, well, let's see, what can I make it? That would work well. I think I'll just make it a float. So float and the default value of 1. Yeah, you'll notice that here, defining this, like for example, actually here, I should probably, first let me finish typing this, then I'll kind of show, just so that Unity doesn't get mad at me and throw a bunch of errors. Amplitude. Oh, yeah, one other thing to know is that the sometimes the syntax does get really weird, and it wants you to capitalize float sometimes, but only sometimes. So so a lot of times, if you are having a bunch of errors in your shader, a really good way to kind of go through it is double check. Wait, should this be capitalized? Maybe it should, maybe it shouldn't. And the last one I needed speed, amplitude, and distance, right? Yeah, distance. Okay, so let's make distance, comma, let's also make it a float. Okay, so we've got these values up here. We've got it messing with it down here in some fancy way. Let's see what that actually does in Unity. So, oh, oops, I have to save it. So as soon as I save, once we head back, looks like we got an error, unidentified. Oh yeah, that's right. I also have to add them here as their values. So they should all just be floats. Here, let me just move this over. Just like before, we also need to, so it's almost like we need to define them twice, because at the top of the script, it's just kind of using the values, but we've got, or it's just kind of like defining them for the Unity editor. So now we got speed, distance. Let's see if it likes that more. Cool. Unexpected token on line 53. Unexpected token star. Oh, there it is. Put an and there. There we go. Okay. So now things are about to get kind of funky. So we'll notice here we have the transparency, speed, value. I'm actually going to take this tint. I'm going to turn it off so we can see it. And whoa, what's going on? So first of all, it's not moving all the time, but sometimes it's moving. So here's a bit of the deal, right? The shader is now drawing the otter differently, right? But what's important about that is that doesn't mean that Unity is always drawing it like that. Something we can do, though, is up here, it'll actually tell us what we want this viewport to do. And you're going to notice here, you can decide, well, I want to show the post-processing and all those other effects. I'm going to hit always refresh to tell it to always do that. And boom. So whoa, you may be thinking, that otter is going crazy. Yes, so actually also turn off the transparency just so we can, it is off. So what happens is, every single vertex is now, its position is changed based on that find function, right? So as a result, it's going all wavy, and it also has the time, right? If we increase speed, so if we increase speed to like 20, then it's gonna get really wobbly, right? Because all the vertexes are all moving based on the sine wave, right? So if we didn't change this, like if instead I didn't want it to always refresh and I was just okay with it doing refreshing whenever Unity felt like it, when I hit play, it would still refresh all the time. So let's see if it reloads the script assemblies. Something that is kind of useful is that the shaders aren't compiled the same way that the C# scripts are. It doesn't go through the whole library. So when you edit the shader and you go right back, well, it will it'll update kind of faster than having to recompile your whole code. So as you can see in runtime, it still always does that. But so something that's kind of interesting then to note is if we put on always refresh, or even if we don't have it on, is that right now something is moving on the scene, but the game isn't running. There's no actual game logic or any Unity scene logic that's actually deciding what to happen. So that means that the otter itself here, its hitbox and its vertices and its mesh is still all entirely the same. Nothing of that has changed. So if in the scene we have like a hitbox, or we have something that detects when we hit the mesh, or a ray trace, it's still going to detect exactly those vertices and all that kind of stuff. This is all extra kind of jazz that we added on only when Unity said, okay, we're done with this data, we've simulated it, send it to the GPU. Then the GPU does all this stuff. So it's only this way on our screens, not actually in the logic. And that is kind of like an interesting artifact of shaders. And we can also mess with this. Like if we turn up distance even more, then it gets really funky. So that's kind of one fun way that we can mess with stuff. Now, let's see what else we might want to add here. So actually, there's a bunch of different ways that we can mess with this even further, right? Specifically with stuff like with the color and what we make the color do. So why don't we kind of start trying something like that? So let's say that I want to have it clip out certain parts of the color, right? Let's say, okay, only draw this pixel if it's red, or only draw the red part of this pixel. We can kind of do that too. So let's add something for that. Let's add a cutout threshold, right? So let's start at 0.2, and this threshold we're going to use later to decide whether or not we add in a pixel. So let's scroll on down. We should also probably add it here. And what's it actually going to do is down here. So like I mentioned, let's do something where if the pixel isn't red enough, get rid of it, right? So for example, just for red. So Unity actually has a function that does that for us. That's called clip. So it'll just say clip r minus. So it's basically saying for this color, ignore the whole color if the red is less than this cutout.threshold. It's a very funky kind of syntax. This is also actually the same though as saying something like so they used to have this other way of doing it where if color.r is less than cutout threshold, discard, right? That's another strange streamer or script lab kind of bit of syntax. But for now I'm going to kind of keep the clip there. So that might be kind of cool. Let's kind of see what that does and see if that causes a bunch of bugs. Oh yeah, see now the parts of him that aren't red, that don't have enough red, are just taken out, right? If I go down, then he'll appear more. But if I make it go up, eventually all of it will disappear, right? So you can make only the red parts invisible. Or if I change that to instead be white or blue or a different kind of color, I could just make that part of it go. And you'll notice that it's as if those pixels never existed. They're gone entirely, completely gone. And it might also be worth noting that even if our thing didn't have transparency, this, I'm pretty sure, would still do this, right? The pixels would just be invisible to the GPU. So that's kind of cool. Now let's say that we wanted to make a script that had the otter normal 90% of the time, but when we wanted it to, like maybe when it got hit, then it would get all funky, right? Maybe only when it entered something specifically very trippy. So in order to do that, we can make a script that messes with all of these values. But let's add another value here just to make it a bit easier for the script. Let's add something that's called amount. So I also have to add it up here. Underscore amount. Let's call it amount. And because let's say that we want it between 0 and 1, right? Just so it's not like that is one thing, is that you'll notice for a lot of these I'm putting like I'm putting floats instead of ranges. Keep in mind, if you are writing these shaders for someone else, it's always a good idea here to make sure that they can only make it the certain things that you want them to make it. Because if they end up making something like the distance negative or like a color negative and it makes everything go all funky, and then that can kind of fuck. So I'm putting the amount as a range just so that they don't make it negative and you can't apply this negatively. And I'll start with it at 1. Now, way down here, we've got that amount. Let's put the amount here as well. So times amount. So we're going to also, actually, I think I need to have the underscore. There we go. So we're also going to modify it by this amount, just so that we can set amount to 0 while keeping everything else the same. The reason why we're kind of doing it with 2 is so that in the material, we can say, oh, when it glitches out, we want this distance. But also, you could also modify it this way. And let's also mess with amount. I think that might be the only place that I want to put it, though. Yeah. Okay. So now, let's say that we wanted to have, let me just make sure I have everything. Then it doesn't break. Okay. So now let's talk about modifying this in another script. So, so here in my scripts, should be an old. Oh, actually, I don't have it here quite yet. All right, just give me 1 second to load down or to load in. I made a script that would modify this, and it does take a bit of work, so I think it's faster for me to just download it. Give me a sec. Ooh, there we go. Here it is. So I called this, well, this script was actually kind of stolen from a bit of a Unity tutorial that did a very similar thing. A lot of this content was kind of based on that old tutorial and how it works now. But here you can actually kind of see what this will do is it takes this private renderer that is the material, right? So it'll mess with the material as things go on, right? It also has a couple coroutines here that will do things at a certain time. So let's take a look at what happens. It's got this, when it does this glitch, it'll change all the values. So here it does the hollow renderer dot material set float. It'll set the float to specifically, you know, the amount. It'll change the cutout threshold, the amplitude, the speed. You can change any of those variables that you kind of had there. So let's, here we'll notice that right when it starts, it kind of sets this chance of bugging out. So there's like I guess a 1 in 10 chance that it'll be doing this funky stuff. So let me just import this script into Unity real quick. Should be in, here, let me just drag this. Here we go. So now I have this script, and let's, oh, where is it? Let's drag it onto our otter as soon as it loads. There we go. And let's see now, if we run, we should kind of see this start to bug it out. Let's see if it works. I see. So something that's important to note, I forgot about this. It has to go, so here in the script, we get this private renderer and we do hollow component is equal to get component renderer, right? So that means that whatever I put it on has to have a rendering component. So here we'll see it has a skinned mesh renderer here on this this kind of Q part of the otter. So you'll notice this otter is kind of in the, I'm going to remove this component. It's in the FBX kind of format of 3D kind of models. So here is where the renderer is, not on the main object. So let's try adding the script here. Let me just. There we go. There, now it's also got that script, and let's see what that does. There we go. Now he's normal, and then every once in a while he starts freaking out. So one thing is that for this mesh specifically, it's unfortunate that all of that is the red cutout. So let's actually try editing that script a little bit to make it so this cutout threshold, we'll set it to 0. Oh, and I should have stopped playing doing that. Oh, no, I changed it in the wrong spot. I have to open this one. Here it is. Set that cutout threshold to 0. So basically, it's running that coroutine that we kind of saw. So every once in a while, it'll kind of get a random number, see if it's less than 0.1, and if it is, it'll start bugging him out. So now he's only freaking out occasionally, right? So instead, you could set this so that when you mouse over it, it does this, or maybe in other specific situations. But that's pretty much how it goes. So one thing to keep in mind is you may be wondering, like, so when we turn that off and it's normally just doing this, how often it goes through this? Like, how often will it update the pixels? How often will it move the things according to the sine wave? Because we'll notice if we don't turn on always refresh, it'll only do it occasionally. And actually, you'll notice it'll only do it when I click on these kinds of things. Well, this will happen every single frame that we send to the GPU, kind of like I mentioned in the presentation. So if you have something in there that's like a counter, right, that you're trying to count up a number, like in your shader, saying until this reaches, until this reaches 50, keep on doing this. If you're curious about how often that'll happen, then it might be a good idea to import time and that kind of stuff, because this will happen based on the frame rate, which sometimes you can't really control if a game slows down and that sort of stuff. But yeah, so this was a really general kind of showing of what shaders can do and how they work in Unity. But as you can see, the sky can be the limit, right? The number of crazy visual effects that you can create or figure out or determine using shaders is immense. And if you want to do anything very unique visually, it's a really great idea to get into it. This is but a drop in the bucket of how much crazy stuff you can do with them. And as you saw, there were so many different types, so many different keywords and different ways to mess with things that the sky really is the limit. But I think that otherwise is pretty much it for the whole presentation. Thank you so much for watching. If you ever have any questions, feel free to send me a message. My email and contact info is probably somewhere in the EML Microsoft team. So yeah, I'm always happy to answer questions.